Welcome to our first screencast. So in these, in general, what I'm going to try to do is introduce us to the modules, functions, routines, algorithms that are available for us already implemented within the tools that we're using, so within Python. That's typically going to mean within SciPy. If you want to watch this video at full screen on your computer, as noted in the description below, at least hopefully, you should choose 720p so that things don't look too fuzzy. On the other hand, it is useful to go ahead and follow along, so do things yourself as we're going along to make sure that everything makes sense and works and whatnot. Okay, so let's dive right into what we want to do. So as usual, we need to run IPython. I use the boring console. Notice I give it pylab, the --pylab option, to ensure that it loads up everything that we need to make our life a little bit easier. So you should see welcome to pylab and whatnot. Okay, again with various bits of information that we've seen before. Okay, so the first thing that we want to do is we want to load up the existing routines. So we're going to learn about how we do that, how we use some shortcuts, and then apply this to the root finding that we've been discussing in class. So to load any module in Python, we use import. Okay, we need to know the name of the module. In this case, we want to load scipy.optimize. So scipy is the overriding package, optimize is a sub-package inside it, or sub-module. And so we can just load that in. Okay, well, now it's loaded. That doesn't look too interesting. We can look at it. Okay, its name is scipy.optimize, so we have to type that. In this console, if I hit a dot and then hit tab, it shows me all the functions inside here, or everything that's contained inside here. So there's a lot of stuff, and that's, well, we're going to have to delve into that. But before we do that, anytime we want to refer to one of these functions, we have to refer to it as scipy.optimize.whatever. Okay, that's an awful lot of typing. Even with shortcuts, you know, tabbing and whatnot to get it to fill things in for us, that's too much work. So what's nice is that we can import this and give it a different name, so give it an alias. Okay, so for example, I prefer to do something like this, import scipy.optimize as opt. Okay, now I can do opt.tab, and I get all the same information, but now it's preceded just by opt, which is significantly less typing. Now opt was just an arbitrary name. I could stick anything that I want here. For example, I could call it at plot. That wouldn't be a very smart thing to do. This would override the plot command. Okay, the tools will happily let you blow away anything else that already exists, so then we wouldn't be able to use plot to make plots. So we probably don't want to do that. It's best to pick something that doesn't exist, or at least is something that's not at all useful to us. Okay, so we've loaded this module and we've seen there's stuff in it. The first thing that we should do is get information on it. Okay, so we do that. We see, yes, lo and behold, it is a module. Okay. Various other things about it, and then it lists all the stuff that's in it with some description. So there's lots of stuff in here, most of which we're going to ignore for now. Some we'll come back to later. So general purpose optimization routines, constrained optimizations, global optimizations, various other things. Okay, blah blah blah. We're not going to talk about any of that. Fitting, we'll come back to curve fitting in the future. Okay. But for us now, what we're interested in is root finding. And so the basic root finding routines are listed here. Notice some of them look familiar. We have the bisection method already implemented for us, so we don't have to write it. We have this thing called Newton, which does both the secant method and Newton's method, or really Newton-Raphson method. Okay, Rider, which we're not going to talk about, and various things called Brent. I tend to, for whatever reason, use Brent to Q. Doesn't really matter, but it's the one that I've chosen to use, and these are just more sophisticated versions of the techniques that we've talked about, in particular in conjunction with the secant method. Here we put a line between 2 points. Here we do some quadratic thing, and so we'll talk a little bit more about that. Okay, and then there's various other things in here which we won't discuss. So we see that there's something called bisect. What should we do? We should look at the documentation for bisect. We see this is a function. Okay, type is a function, and this tells us how we call that function. So the interesting things here to look at typically is, okay, what arguments are required? So anything that doesn't have an equals with something after it is a required argument. All the rest of these are optional arguments. And again, we should have seen some of these things in the first lab. Here we're just going to go through them a bit more carefully. Okay? There's a description of what this routine does. Okay, finds a root within an interval. Okay, does bisection. Give it a function f, some interval or arguments a and b, and f, a, and b must have opposite signs. That's how we get our bracketing. Okay? And then it even tells us that this may be a slow algorithm, but it works. Okay? Furthermore, then for every one of the parameters listed in here, there's documentation about it, or at least there should be. We see that f is a function, needs to be a Python function that returns a number. Okay, that's an important thing. That's how we need to write our function. Okay, f must be continuous, and of course f, a, and b must have opposite signs to get bracketing, and a and b provide the bracketing. Okay. All the rest of these are optional. They're somewhat interesting and useful. So let's briefly discuss a couple of them. Args is going to be very useful, but we'll come back to that one. There's two tolerances given in here, and we can read about them down below here. Okay. Basically, what they correspond to are an absolute tolerance and a relative tolerance. Okay. The question is, how do we know when we've gotten to an answer? Okay. We're trying to find a 0 for this function f in this interval. How do we know when we're close enough? And that's what these tolerances give us. There's two of them because depending on the value of the root, we can get into situations where one of the tolerances is satisfied but the other isn't. And so we don't want to loop forever trying to search for something that can't be accomplished. Okay? In other words, if the true root were 0, okay, we could run into situations where it would just loop forever unless we have an absolute tolerance in there like x-tol. Okay. Yeah, even given that, there is a max iter in here, okay, which again we can read below. Okay, if the convergence isn't achieved within this number of iterations, it's going to give up so that we don't run forever. Okay. Full output and disp are also somewhat useful. We'll explore full output a little bit in this screencast. Okay. As we scroll down, we see that it also tells us what it returns, and it returns x0, a float. This is the 0 of f in that interval. Okay. It can also return something else called a root results if full output is true, so we'll come back to that later. Okay. Well, let's just look at that again. So remember what this looks like, okay, how this thing is called, because let's look at one of the other routines, brint q. Okay. If we remember what that looked like, notice this looks exactly the same. Okay. That's nice because what that means is that we can freely switch between the algorithm that we're using just by changing the name of this function, and we don't have to change anything else. So that's a good feature in how things should be designed, okay, to the extent that it can be. Okay. So again, we're not going to say too much about this routine, but there's a nice description of it here. You can learn more about it if you want. It even references numerical recipes, hint hint. So we can read about the routine in there. For our purposes, we don't care too much about the details. Okay, we just want to be able to use these. So let's start by applying this to a particular problem, and let's use the one that we discussed in class. In class, we talked about finding the square root of 2. So let's define a function. Okay, we can define a function like so. Typically, we should give it a better name, but when we're doing things quick, we can throw in whatever name we want. Here, I'll just call it f. Again, the argument, this is going to be our guess for the root. Let's just call it x. And so the function that we were trying to find the 0 of was x squared minus 2. Okay, this will be 0 when x is equal to the square root of 2. Notice that when we did this, it automatically indented for us, since indentation matters, so that's kind of nice. It recognizes the return statement probably means we're done, so it moves us back to the beginning. So we could type other things if we wanted to find multiple functions or something, we could do that. But we're done, so we just hit return. Okay. Now, we can evaluate this function at the endpoints we had discussed in class, 1 and 2. That's going to bracket our root, and we see that, yes, lo and behold, we do have opposite signs as required. So now we can just call this routine. We feed it f, we feed it a and b, our interval, we run it, and lo and behold, it returns the square root of 2. To see that, perhaps an easier thing to do is to square it. We see, yes, that is really close to 2. Okay. As also stated, we can easily switch routines, don't have to change anything about the arguments. And again, that gives us the square root of 2. If we compare these two numbers, they look very similar. Okay, again, we can square this. We can see that, yes, this also is 2. Now, of course, there's a small difference between them, and the small difference is related to the tolerances. So if we wanted to improve the number of digits that this gets, we need to start playing with those tolerances, and I will leave it to you to do that. Okay. For our purposes, though, this shows us how to use these routines. Okay, so we can use either one of them. Why does it matter which one we use? You know, what's the big deal? So for that, let's go back to the documentation and look at the full output, or look at the return value. So again, if we don't give full output, it just returns the value, which is great. That's typically what we want. But if we want more information, we can use full output. So as it says here, full output, okay, if it's false, it just returns the root. Okay. If it's true, then it returns this thing, okay, x comma r in parentheses. Putting it in parentheses means that this is a tuple. Okay, tuple. Okay. A tuple is a read-only list in Python. Okay. In other words, this is how we return two different things. Okay. X here will be the root, so this will be the same as what we're used to, and R will be something called a root results object. Now down here in the return section, it does tell us, in particular, R dot converged is true if the routine converged. So it's going to give us a way of determining whether it converged or not. Okay, so once again, typically the best thing to do is to just play with this and see what it does. So we're going to set full output to true, and lo and behold, it returns something in parentheses, the root, and something called root results. Okay, so that's not very useful. So let's store those. So to store those, we use the same notation as it told. We give it two things inside parentheses, and what it will do now is fill in these two slots with these return values. Okay, the names don't matter. I can call these whatever I want, but root and info seem useful because root is, lo and behold, the root, and info, lo and behold, is yes, this root results thing. Okay, well, the first thing that we should try to do is get documentation on it, and it's a root results. Yeah, so that's not so useful. There is no documentation string for it. That's somewhat unfortunate. Although, honestly, the reason why is because it's a simple thing. It's just a simple container, a class or an object if you prefer, that contains information. And in fact, the documentation had told us that there's going to be something called converged in here. And it's going to be true if the algorithm has converged. And lo and behold, this has converged. We see that there's other things in here, so it's useful to check those. We can look at flag, and, well, what do you know? Flag is converged. So I guess that also tells us that it converged. We can look at root. What do you know? That's also the root. So this object itself contains all the information. What's of more interest to us, though, is the function calls and iterations. This tells us how much work it had to do to get the result to the desired precision or desired tolerance that we asked for. So we see that it had to call the function 42 times, and it required 40 iterations of the algorithm to do this. Okay? So that's a lot of work to do to just find the square root of 2. Now for our simple function, okay, we don't really care. I could call it a million times, and we probably still wouldn't notice that it took any time. But if we had a complicated function, we would care a lot about how much time this is being spent. Or if we had to do this billions, trillions of times, we would care how much time is being spent in the algorithm. Okay? So we do, so this is going to give us some idea of how much work is required to find the result. Okay, so with those numbers in mind, let's now do exactly the same thing with Brent Q. Again, we could check all of the things, but let's just look at function calls Woo, 8. Let's look at iterations, 7. Okay. So BrentQ required far fewer iterations, far fewer function calls, factor of 5 or 6 fewer, to get the same or to get comparable resolution. And so this is showing us the advantage of using a more sophisticated algorithm. Okay. It requires far less work to get the same results. And that's, again, the benefit of using, or typically a benefit of using a routine like this. There won't always be benefits, and we'll, again, see things like that in the future. Okay, so that's great. Okay, so we've explored some of using these routines, and again, we should become familiar and comfortable with doing that. But we've set this up only to find the square root of 2. What happens if we wanted to find something else? Say, the square root of 3, or the cube root of 4, or the 10th root of 9, or anything like that. Okay? What we would have to do now is we would have to go in and change the function every time we wanted to do this. So if we wanted to find the square root of 3, we'd have to go in and change this to a 3 and then rerun everything. That's far too much work. This is where args comes in. Okay, so let's again look at the documentation. There's this args where we can feed it something in parentheses. We now know that that means a tuple. Okay, so a read-only list. So if we look here, in fact, it tells us it's a tuple. It's optional. And this contains extra arguments that are sent to our function f, and the way that it does it is like this. Whew. Okay, so that probably doesn't mean too much to us. So this isn't a great, well, there isn't really a great way to write it. What it really means is we're going to take the function, we're going to feed it x as the first argument. Remember, x is our current best guess at the root. And then what it's going to do is it's going to tack on the rest of the arguments in exactly the order that we give them in this optional thing called args. Okay? Okay, so again, probably the best thing to do is to just do an example. So let's write a more generic function called nth root. Okay, that it will take the nth root of some number. The first thing that gets fed in is x. So let's just call it x. Again, remember this is our current guess. The next thing, let's choose y. Y will be the number that we're trying to find the root of. Okay, again, maybe we should give it a better name, but this will be good for now. And n will be the root that we're trying to find. Now we can give it optional values, we can make this argument optional by giving it a default value. Any argument that's going to take a default value has to appear after any that doesn't. Okay? These can then appear in any order, but let's set n equal to 2. So what this means is that by default we're going to look for the square root of y if we don't specify a value for n. Again, maybe the best thing to do is to write out what we mean by this. What we mean is this. Okay, so again, if we want to find the square root of 2, we set y equal to 2. So 2 gets put in here. N equal to 2, which is the default, so n gets stuck here. This would be x squared minus 2, just like the function we defined before. Okay. Now we can call bisect with nth root. Okay. We can do, let me expand the interval since we're going to play with a few other cases. So let's now do 1 to 5. Now we can feed it args is equal to 2, and in fact we have to give it an argument because nth root expects 2 arguments. So let's feed it 2. Notice I don't have to specify n. If I don't specify n, it takes the default value, which is 2. So this will find the square root of 2 exactly as we had found before. Okay. What's nice now is if I want to find the square root of 3, I just change this number, and lo and behold, that's the square root of 3. Okay. If I want to find the cube root of 4, I put in 4, and now I also specify n. Okay. So since this appears here, this will be the third argument that gets put in, so that will be n, and so that will be the cube root of 4, which again we can confirm by cubing this. Okay. Again, just to show, if we want to switch algorithms, all the arguments stay the same, and this also finds the cube root of 4. Okay. Notice that even though I gave it a name here, this is, if you like, a named argument, or really what's called a keyword argument, I can also specify this, or I can try to specify this as the keyword, but that doesn't work. Okay. It tells me invalid syntax. Okay. So despite the fact that I gave it a default value and I'm trying to treat it as what's called a keyword argument, if you know something with Python, we can't do that. We still have to specify it in the order given. Okay. So that's one detail. I guess I should have warned you that was a detail that maybe you don't want to worry about. I guess one other detail that I'll mention now is, so for me it worked by just sticking a 4 in there. And that will work in most cases. We'll see many functions that we call, many scipy functions that we call, where we feed it a function, will take optional arguments in the same form. Sometimes when we feed it a single argument, it complains. It gives you some obscure error. Okay. The reason for that is that args needs to be a tuple. Well, how do we force this to be a tuple? Well, we can stick a comma in there, and what that means is that yes, this really is a one argument tuple, not just a number that I happen to stick parentheses around. Okay. So again, this is a detail. If you run into an error, or if you just want to be careful, we can always just specify it like this. And again, this is calculating the square root of 2, which, well, sorry, this is calculating the square root of 4, which is just 2. Okay, so now we could go crazy using this to find roots of anything that we wanted to. Again, what this is supposed to be showing us is how to use these general routines, okay, and how to load them in. And so going forward, we're now going to assume that we know how to do this and start using some of these more advanced routines. Now, we didn't talk about most of the things in here. We didn't even talk about all of the root finding ones. We should do that, for example, with Newton. Newton is slightly different, as we discussed in class. In fact, this contains both Newton-Raphson and secant method. In this case, we only need to specify one number, x0. We can choose to specify another function, f prime, which is the derivative. If we don't do that, then as this says, it uses the secant method. If we do, then it uses Newton-Raphson. Again, there's a tolerance in here, a maximum number of iterations. We can even specify a second derivative if we like. In that case, it uses something called the parabolic Halley's method, which we haven't discussed and will not. But again, this is showing one of the benefits of using existing, well thought out, well tested routines. They can implement many more sophisticated things than we're typically interested in. Okay. So again, you will end up using Newton at some point, so you should play around with it a little bit on your own to get used to using it. Okay, so that will wrap up things for today, and in the future we will try to continue doing things like this to introduce us to these ideas and then end up using them in class without having to go over all these boring details that are better spent or better done by you in your own free time. Okay, see you in class.